And this one involves X centers. And this one is like you define these 3 points symmetrically and you show they're collinear. So which one do you guys want to choose?
Let's do the symmetric one.
Okay.
Yeah.
So this one, right?
Yeah.
All right. So we have a triangle with circumcenter O. A1 is the midpoint of BC. And then we draw the circumcircle. And it meets it at A2, AA1. So this is A2. A lot of these problems I solved using Desargues' theorem. Oh, whoops, that should be A2. Okay. And we draw the perpendicular from A1 to AO. Let's draw the center. I'm going to draw that ray. And then, whoops, sorry, perpendicular. Okay, so this is QA. Let me make some room. PA lies on QAA1, such that PA2 is perpendicular to A2O. Okay, so basically just on the tangent, I guess they're just saying draw the tangent to the circle and then see where it intersects that. Okay, so let me shrink this. This is PA, and then we define PB and PC the same way. And we want to show that they're collinear. That seems kind of random. So yeah, there would be, I don't know if we want to draw all of them. Although we could probably. Yeah, I'm going to draw all 3 of them just to see. Okay. So we're going to want midpoints are B1 and C1. Some radical axis. Let's draw the rays. So yeah, really we want to draw all these rays. Okay. This is B2. And this is C2. And then we draw the tangents. Is this the same idea where we draw 3 tangents and we make it into a triangle? I don't think so, but
I don't think we're gonna use it again for the 3rd time.
you think we might?
No, not for the 3rd time.
That would be crazy. let's see. So we do that, and then we need to draw perpendiculars. So let me draw the in-center. Oh, that's not like the in-center. That is the centroid. Okay, hold on just a second. Let me finish drawing the rest of the points. So I drew, so Q, so I drew the perpendicular from A1 to AO. I'm going to need to draw the perpendiculars A1 to AO, B1 to BO. Whoops. I don't know what's happening here. So, oh, because that was a perpendicular bisector. Perpendicular from B1 to BO, it's QB. And C1 to CO. And that would be QC. Like there. Let me make things look a little better. I'm going to hide a bunch. Okay. So this is perpendicular, and this is perpendicular. Okay. And PA, so once we have Q, we draw the line through that, and we see where it meets the, oh, okay. Actually, I shouldn't have hid this. I should have drawn the whole line. So QBB1, I should have drawn the whole line and then see where it meets this tangent. This is PQ or PC. And the other one I think is going to be super far away. So it's going to be where these two intersect. Okay, so let's see if I can make that visible on the screen. It's kind of hard. Let me make it like a smaller triangle. Yeah, it's very hard to do. Let's think about the best way to do this. So I could try to make it just like a really small triangle, maybe lower B and C a little bit. And yeah, it's very hard to make these intersect. I'm going to keep trying for a little bit. If I really can't do it, then maybe I'll just draw two of them, but just let me try for a little bit more. Yeah, this is going to be hard. I might just have to draw two of them. And then the other, yeah. Because yeah, otherwise the diagram just doesn't look good. Yeah. I'll just keep it like this for now. And then, yeah, you'll just have to know these two intersect at PB. So this line is
PA, PB, and PC lies on the radical axis of the circumcircle ABC, and it's 9-point circle.
oh, okay. So I'm going to draw the 9-point circle. Yeah, sorry, I didn't get to that yet. Just, okay, hold on just a moment.
Maybe we just keep PA, and we don't have to draw PB and PC.
Okay.
Yeah, that's how
So,
we work with it.
all right, let me draw the 9-point circle. So basically you said PAPC lies on the radical axis of these two circles?
Yeah.
Or it is the radical axis?
Okay.
Yeah. You think A1QA is tangent to the 9-point circle? Well, if we know it's the radical axis, that like solves the problem, right?
Yeah, exactly. A1 QA, A1, yeah, it is tangent to the 9-point circle. That's how I solve it.
Okay, so let's see. A1QA is tangent, and then we're saying B1QB. Okay, so since they're all tangent to the 9-point circle, then
We can show that PAA1 equals PAA2.
that they're isosceles, yeah. Interesting. Okay, so let's see. So first of all, how do we show? Yeah, so I'll draw the 9-point center in. So we call it N. We want to start by showing. We want to start by showing that QA1 is tangent. What's the best way to do that? So we could calculate this angle, right? It's 90 minus angle A1AO. And just angle chase to prove that PA1. Yeah, so we could use an angle chase to show that this is isosceles, and then use the fact that NA1 is parallel to AO. Oh, okay. So that's really the key. NA1 is parallel to AO. And NB1 is parallel to BO. Okay. So this might be a really dumb question. Why is NA1 parallel to AO? Is it just like an angle chase? Is it some homothety?
You should label the ortho center of ABC, and you'll see, I think.
Okay. So this will be the orthocenter. One sec, guys. I'll be right back. All right, I'm back. Okay, so NA1 is parallel to AO because AO is translated to NA1 by a homothety about G. Okay. So if we know that, then we could prove this is tangent because angle N, let's see. We want to show, because that would mean NA1 is perpendicular to PAQA. Okay, so yeah, that pretty much solves it. So first of all, let N be the 9-point center. And then by a homothety about G with ratio 1/2, we find that NA1 is parallel to AO, or -1/2. All right. And so this means that NA1 is perpendicular to PAQA. Which means that PAQA is tangent to the 9-point circle. I'll write it like this, be the center of the 9-point circle omega. So I'm going to give it a name. And this means that PAQA is tangent to omega. And then not only that, it's obviously tangent, but to the bigger circle. But we want to show that this is isosceles, and that should just be an angle chase because angle PA-A1-A2 that's going to be equal to angle A-A1-QA. And that's 90 minus A2AO. Let's see. And yeah, we want to show it's this. We want to show that this angle plus this angle is 90. And that's true because AO is like a diameter of the circle. So yeah, 90 minus A2AO is angle A2 A2PA. That's an easy enough angle chase. Okay, so I kind of skipped a tiny angle chase there, but I think the viewers can figure that out. So PA, A2, A1 is isosceles. So two. Okay, so P has the same, PA has the same power with respect to those two circles. Omega and the circle ABC. And then similarly, PB and PC have the same power, those circles. So PA, PB, and PC are collinear on the radical axis of those circles. Okay, nice solution. I like it. PA, PB, and PC are collinear on the radical axis of those circles. All right, so I'm going to move on to the next one. Let's see. So we did this, we did this. Let's see if we can do this one quick. So we have an isosceles triangle. AB equals AC. And then we extend this, so we draw a ray. Call this point P. X and Y are in AB and AC, so PX is parallel to AC, and PY is parallel to AB. That's kind of interesting. Almost makes it look too easy. So we draw the parallels to those two. I feel like I might have done this problem before, actually. I don't remember. Okay, so we need to draw the whole ray AC and AB. So yeah, we have a little parallelogram here. So this is X, Y. T lies on the circumcircle. You know what? I think I did this on my channel already. Yeah, this is just I ran. Okay. BAT. Let me just make sure. Yeah, so I think this is a diameter, AE, and so BAT equals CAT. Yeah, I did this on my channel before. And I think it's easy to do. So yeah, I'm not even going to write it out, I don't think. I think it's easy enough to show that if T is the midpoint of arc BC, then Tx squared minus Ty squared is Px squared minus Py squared. Because Px squared is Ay squared, and Py squared is Ax squared. And let's see. But yeah, I already did this one, so I'm not going to do it again. You want to try an isogonal conjugate problem? Let's see. I actually think this might be well known. I think we might have done something like this before. Let's try this one. So we have two circles. I kind of like this one. Two circles are externally tangent at T. How should I draw this? Let's just draw a line through AB. Then we have a point on one of the circles, X, and we draw the tangent at X. And we want it to meet the other circle at 2 points, A and B. Oh, whoops, we should call these, we'll call it O1 and O2. So they don't say which is A and which is B, but I don't think we need it for the problem. XT meets the circle at S. What's circle omega? I'm guessing they mean omega 2. I'm going to assume that for now. So this is S. And then C lies on TS. So this arc, I guess C is any point. YC is tangent to the other circle. So X can be any point and C can be any point. So this is Y. And I is the intersection of XY and SC. Let me move point C around, so kind of like that. So first we want to show that CTYI is cyclic. And then we want to show I is the X center of ABC. Okay. All right. So CY was tangent. And SC and I are collinear. And then these are tangent. Okay. So we want to show I is the X center of ABC. I think I did something like this before, but I forgot the solution. So let's do it. Are BT and I, no, BT and I aren't collinear. So yeah, is it obvious that BI bisects angle ABC? Could we use the in-center, X-center lemma? I don't know if it's worth drawing the in-center of ABC. It's probably not a bad idea. Let me do that. Let's draw the in-center of ABC. That'd be D. So we kind of want to show ADIC is cyclic.
Did we solve part A?
Oh, no, actually we didn't solve part A. I wonder if that's just like an angle chase. Let's see. Okay, that's trivial by an angle chase. So angle IYC is angle XYC, which is half of this arc, and angle ITC is, let's see, maybe there's a better way to do that. You could break ITC into two by a tangent at T. Ah, that's a good idea. Okay. So it'd be ITE plus ETC. How do you find ITE though? Oh, try using YIC instead. Oh, so YIC and YTC. So YIC. How would I find angle YIC? YIC is YIS, which is YXS plus XSI. Ah, and that sounds good. Okay. So that angle chase would prove that this is cyclic. It's a good idea using that third angle theorem. Okay. Because yeah, XSI is half of this arc and YXS is half of this arc. Yeah, it's the same arcs. Yeah, I see how it works. Okay. Yeah, exactly. Yeah, that was a good idea. Breaking it up like that. So that proves that this is cyclic. And see what we do after that. So yeah, I could type it up. So let the tangent to both circles at T meet YC at E. Then we have YTC is YTE plus CTE. So which is equal to, so yeah, YTE is YXT. And that's going to be plus angle TSC is equal to angle YIC. So CTIY is cyclic. Or I'll say YITC is cyclic. Okay. That solves that. That's part A. We'll just add an A here. Now for part B, let's see what we can do. So we want to show AI as an angle bisector here. Yeah, I guess there's two strategies. One is to use the in-center x-center lemma. The other is just to show that it lies on angle bisectors, right? Yeah, I feel like I've seen this kind of idea many times. I just don't, my memory is really bad. I remember, my memory is good enough to know I've seen it before, but not good enough to remember how I did it. So if we want, basically, we could draw the midpoint of this arc. I'm going to cheat here a little bit. So if this is the midpoint of the arc, we could try to show that B, F, and I are collinear. We know that B, F, and V are collinear. Or we could try to show that angle O1AD is 90. Or sorry, IAD is 90. Let's see. I wonder if we could redefine I, like, what if we define I some different way and then we show I as the X center? And then I feel like this might be like a phantom points problem. Are T, E, and F collinear? I don't think so, but no. Yeah, I want to define I in a different way. Like what if I let the angle bisector here meet AY at I prime, and then I show that that's cyclic, and then I try to show that somehow it's the X center. So first of all, if I draw this ray, if I draw ray BC, can I show that CI is the external bisector here? Is that just an angle chase?
I think we can prove that. I think we should prove that SAE is equal to SB because SB square is equal to SA square and is equal to ST times SX.
Okay, so say that one more time. We should show that SA equals SB.
Equals,
sorry.
Yeah, it is. We have SB square is equal to ST times SX.
ST times SX.
Yeah, because we can show that STB and SBX are similar.
Okay.
Because angle TXB is equal to angle TBS, and they are both equal to angle XYT.
They're both equal to XYT. Okay, so tell me one more time the two triangles that are similar.
I think I'll type it out.
Okay. SB squared is equal to ST times SX. STB is similar to SBX. Okay. That's interesting. Because angle TXA, let's see. So STB is similar to SBX. So it's kind of well known. I guess you're using the fact it's like well known that so XT meets this circle at the midpoint of this big arc AB. So yeah, that makes sense. So you're using that fact. Okay. So we know that SB squared is ST times SX. ST times, yeah. So SB is basically the length of the tangent to the circle, to that circle. All right. That makes sense to me. So yeah, let's see, where would we go from there? So CI is the external bisector. SB, do you mean SB equals SA or SB equals SC? Yeah. Okay. Yeah, okay. So since SB is equal to SA, so yeah, you're saying SCB is SAB is SBA is ICA. Yeah. So oh, SB is equal to SI. Why is that true?
Because just keep using those similar triangles.
Okay.
They prove that SRT is equal to SX.
Okay.
I don't think it's really that hard, but maybe just keep using angles and figure it out. So
Okay. All right, so I'm going to write up what we've said so far. So first of all, SA is equal to SB. That's true by an angle chase. Let me see. So we have SAB is STB, which is 180 minus XTB. And we want to show that yeah, so I'm trying to figure out, so I found one way, like if we draw this tangent line and we let it meet AB at another point, I can use that to show SAB as isosceles, but I don't know if there's a faster way to do it than that. So oh, SBA is, yeah, I think it is fast. SBA is equal to angle XTA. Oh wait, actually, SBA is XTA. And SAB is, wait, how do we, like, I know one proof that SA equals SB, but it's kind of long. Like, is there a shorter way to prove that SA equals SB?
like I said, SI square equals SB square equals ST times SX.
Okay. But I thought but like to prove that SA equals SB, is that obvious?
I just said how we did it, like using the fact that the archetype, you're using those two similar triangles. Yeah. Let me write it for you.
But don't you prove that those are similar by like, don't you prove that those are similar by first?
I prove it to be similar because SBT is equal to angle SXB.
SBT is SXT, is SXB, is what you're saying. Let's see. STX is a straight line. SO2 is parallel to XO1. Oh, I think that's what I was missing. Okay. Yeah, SO2. So yeah. Let me start out saying that. So B. Yeah, I had a more complicated proof, but yeah, that's the better way to do it. So SO2 is parallel to XO1. And that implies that SO2 is perpendicular to AB. And that means that SA equals SB. Okay. So we have this, and then so SAB equals, so yeah, STB equals SAB equals SBA. Yeah, so we know CI is the external bisector. Okay, actually, I'm going to write that out first. So angle SCB equals SAB equals SBA equals ACI. So angle SCB SAB is angle SBA is equal to angle ACI. So that proves basically that CI is the external bisector. And then these two show the similar triangles. So one second, I'm just going to write this out. What was it? STB is similar to SBX. And then now we claim that SI is tangent to the circumcircle of TIX. And that's the proof. So SIT is equal to IXT. Okay, see you next time, Con. Yeah, thanks for joining. Thanks for sticking around so long. All right. So, okay, so SI squared is equal to SA squared is equal to SB squared. So I'm going to write that out. So yeah. Let me just type out everything you've written. Oh, but so I think this is also, because then we have SB squared is equal to ST times SX, which is equal to SA squared. Oh, but SI squared, we also need to show that. Okay, so I'm gonna write out the angle chase that you wrote. Okay. Since SIT is IXT, we have another pair of similar triangles. And so then we can get that. Okay. So yeah, so S is the circumcenter of IAB. Sorry, okay. So I'm gonna keep writing out, hold on just one sec. S is the circumcenter of AIB. Now we observe, so ABI is equal to IBC. So that would solve it. Okay, so ABI is ASI. Oh, ABI is twice ASI, which is twice ASC, which is twice ABC, which is A. Okay, interesting. So, okay, I like the way you wrote that. So this basically solves a problem because we have, okay, so angle ABI, that's twice.
ABI is twice of ABI is ASI.
Oh, it's the other way. Twice ABI.
Yes.
Yeah.
Yes.
It's ASI. ASC. And this means that angle ABI equals angle IBC. IBC. And basically that solves the problem because yeah, once we know that, basically I is the X center of ABC. Because it lies on two of the three external angle bisectors. This is interesting. So yeah, I like that we used, yeah, really the key is that S is the circumcenter of AIB. Once you know that, a lot of the angle chasing becomes much easier. So yeah, we use this to prove that SA equals SB. Interesting. That's where we use that they're externally tangent. So yeah, there's a lot of good stuff that went into this. Nice solution. So I am going to, did we do all the others? Oh, there's this Vietnam one that was kind of hard. We could just take a look at it. Maybe part A is doable. Let's see if we can get part A. So we have a parallelogram, ABCD. and AC intersects BD at I. So that's going to be the center of the parallelogram, which is the midpoint of the diagonals. G is inside triangle ABC, so that IAG is equal to IBG. So let's label this as I. So we want IAG to equal IBG. This is always really tricky to do. I don't know of a great way other than, here's how I usually do it. And yeah, maybe there's a better way, but actually, you know what? Let's do it like this. So what we could do is we could draw the angle bisector of AIB. And then I'm going to reflect a couple things. Yeah, actually, you know what? Let me do it like this. So okay, so actually, yeah, that was okay. So I'm going to reflect E over the angle bisector. And then I'm going to draw the parallel from A to B prime E prime. Let's make this look a little taller, this parallelogram. But I don't want it to look like a rhombus. So yeah, not too tall. And yeah, we draw where B, let BE and that point intersect at G. So this is G. And then IAG equals IBG. Let's hide everything else. I'll keep point E just in case. So IAG is IBG. Let's see. Okay. And let E, I'm guessing I should say E and F, probably. Let E and F. So the projections of C on AG and D on BG. Okay, so let's draw the rays. See if we can make this look better. Oh, what was this? Yeah, let's just try this for now. So this should be E and this should be F. Let's see. How do I make this look better? Do something like this. And then I'll just leave it like that for now. What was K? Or actually they use K, I'm gonna call it R. What do we want to show? The E median line of triangle BEF. So basically we want the midpoint of EF. Let's see. But maybe part A is doable. Let's just look at part A. I don't know for sure, maybe it is hopeless, but let's give it a try. This almost looks isosceles, this triangle. I wonder if that's true. No, it's not true. Okay. So basically we take triangle BEF. Oh, let me delete this. Can I move C? Yeah. Let's see, maybe I can move R. Maybe like that. That looks okay. Okay. Oh, but then, so we want the E median of BEF. So we need like the midpoint of BF. And then the F median of AEF. So then we want the midpoint of AE. So we take the midpoints of BF and AE. I hate how that's so close. I want H and J to be like a little farther away from G. Okay, so let's draw those two rays. The E median of BEF, so that would be EH, and the F median of AEF. And those are supposed to meet at H. I already used H, oh well. Let me call it S here. So if we call this H, yeah, this looks kind of hard actually. We want to show that AF BE and IH are concurrent. It feels like this args, right? At least to me it does. FHJ, whoops. Okay. Test chat. Yeah, the chat works. AF, BE, and IH concur. So that's A. Yeah, we don't really need R. I'm going to hide it. Let's see, can we use the SARGs? So AF, BE, and IH. So those are concurrent. So can we say triangles AFH and BIE? Let's see. Can we use the SARGs on those? Well, no, we would want, so we want AIB and EHF. Basically, can we use the SARGs on those two? So then we want to see where A, B, and EF meet. And yeah, this is going to be pretty hard, I think. Just going to try to make a nice diagram. Maybe a tall, I feel like a tall parallelogram is much better for this, I feel like. And it's hard to do because the problem statement is kind of long, but yeah, that looks much better, I feel like. I wonder if IH and G, no, IH and G aren't collinear. So yeah, we'd have to use that angle IAG is IBG somehow. So basically those two triangles are similar, DFB and CEA. Yeah, DFB and CEA are similar. And this is cyclic. Well, actually, it almost looks like J and S are the intersection points when they're not actually. So yeah, I think that we really want it to look something like that, probably. Yeah. That's better. So J is the midpoint of AE, S is the midpoint of BF. So basically IS is parallel to DE. And IJ is parallel to CE. So yeah, these two triangles, IJA and ISB, are similar. Is ABEF cyclic? Let's see. No, because FAB looks like maybe acute or close to right angle, but this is definitely acute. So IJA is similar to ISB. That's got to be useful. And so let's try the SARGs again. So we'd want EF and AB. Then we'd want EH. So basically, if we label, we're saying that if we label these two intersection points, which are kind of hard to see, we're saying it's collinear with the intersection of EF and AB. Yeah, this is a fun one. There's not that much information, but apparently it's pretty hard. All right. But yeah, other than Desargues, I'm not sure of another way we would solve this. It's pretty interesting. So we could say let I be the center of the parallelogram. So if I is the center of the parallelogram, drop perpendiculars to AG and BG. But yeah, you still need point F. Any harmonic bundles? I'm not sure.
But if we take a harmonic bundle A, J, E and point at infinity and try to project it back to the main cyclic quadrilateral we have in the center, something like that.
Okay, so this one, so AJ, E and infinity, and
Is IE tangent to this or something?
let's
Does not
see.
look like that.
Yeah, I don't think IE is tangent.
This one sounds hopeless.
It almost looks like that's probably a coincidence, but I don't, if those concur. Yeah. All right, I think I'm going to stop here. This looks like a fun one, but it's pretty difficult. So I'm probably going to keep working on it after the session. Thanks to all the people who participated. I know it's kind of long sticking around for these sessions, but it was good to see everyone. So if you'd like to join us in the future, feel free to send me an email at mgreenb801@gmail.com. It's going to be in the description of my video, and we do it every Sunday at 8 a.m. US Central Time. So thanks again for watching and have a great day.